Okay, so another section dealing with circular motion, and uniform circular motion really, is section 6-5 of the textbook. Make sure you read that and look at the PowerPoint. We just saw from the previous section acceleration towards the center, I could usually call it radial acceleration, is v squared over r for uniform circular motion. That means constant speed. Uniform circular motion. So if there's an acceleration, there's got to be a net force. So just extending this a little bit, the net force turns out to be ma, just Newton's second law, but it's radial acceleration towards the center. So we could rephrase this as mv squared over r. That's got to be the net force towards the center if something's going in a circle with a constant speed. This is what the net force is. So just like we did with all the different problems we've worked on this year with Newton's second law, you could write this, you're completely correct, and then you have to look at the picture and find out, well, what is this actual force that's towards the center? Another thing you can usually use with this is the speed is 2 pi r divided by the period, also 2 pi r times the frequency. Rather than do a homework problem, I want to do sort of what the lab is going to look like this week, and it's going to utilize this whole idea. And let me do that for you now. Do a little bit of erasing here without ruining the board, hopefully. And what we'll do in the lab is we'll have a setup like this, and we'll have a mass that's attached to a spring. Could have the drawing off just by a little bit. And this mass is actually over here if it's not spinning. So with the lab, this is free to spin. So we'll rotate this. The mass is kind of hooked up like this. It's just not floating. But it's also got a spring on it that pulls it back that way. So when it's not spinning, it's somewhere over here. It's pulled over here. But what you'll do and your group will do is spin this. You'll measure this radius. This is spinning in a circle at a constant speed, and you'll be responsible for that. You'll learn more about that Thursday. So there is going to be a force towards the center provided by the spring. And there's also, tension here and mg here. But it's this spring force back towards the center that provides for the centripetal acceleration, the acceleration towards the center. So we have the net force is ma, radial acceleration, mv squared over r. Good, and we could actually figure out what this force is by looking at this part of the equation. So m, here's the r. Now I'm going to work with this v squared part. Distance around would be 2 pi r divided by the period, and I could square that. That's perfectly good. So we have an m divided by r. This is the speed from this equation squared. So 4 pi squared r squared divided by t squared. One of the r's cancels out. So the force towards the center then would be 4 pi squared m r divided by t squared. So 4 pi squared m r times the frequency squared. So just by knowing what the frequency is, and that's something that you'll measure, measuring the mass of this, we'll call that the bob, and measuring the radius, we could calculate what that force would have to be back towards the center just by looking at the period. We could figure out what the force is back towards the center. And then later what we'll do, when it's not spinning, we'll be able to calculate what this force is by hooking this over a pulley situation. So yeah, let me give myself some room. So that was the rotational part of it. So when it's not rotating, we're going to stretch the spring out by hooking a mass here, a weight, put how much weight we need, more and more and more until this bob is lined up right over this indicator. Good, and that's the radius right out to there. So we'll, this isn't spinning anymore, put some mass on this hanger, it'll pull it down, down, down. So at that point, we can figure out what this force is, this force of gravity, the weight of this. So whatever this weight is equal to the spring force back that other way. So we'll calculate the spring force by looking at the rotation and the frequency, calculate it that way, and then compare it to whatever this weight turns out to be. So weight, get the mass of this, multiply it by g. So whatever mass is on there times g. This weight is equal to the spring force. That's sort of the theoretical spring force. And then we'll compare that to the spring force we measured by measuring the frequency, the mass, and the radius. And then depending on what the lab says, you can sort of change it up a little bit. Good, so chapter 4 was centripetal acceleration. Chapter 6 is taking it one step further, multiplying that by mass. And we'll do some more problems with free body diagrams and things like that. So make sure you look at the PowerPoint dealing with circular motion. Thanks.